Hi everyone. In this session, I will discuss behavioral modeling, which is one of the most important concepts in Verilog. In this session, I will discuss up to the conditional statements, and in the next session, I will discuss what are conditional statements and what are the looping statements that are available in Verilog. So this session will mainly focus on how to use the initial and assign always blocks and how to assign the statements, procedural statements, all these things. So let's begin. So these are the contents of the session. First, I will explain what is behavioral modeling, and then I will move to what are the different kind of structured procedures we have in behavioral modeling, like always and initial, which are very important in Verilog. And then I will move to blocking and non-blocking assignments, and I will show you the difference between blocking and non-blocking assignments with some examples. Then I will show how to control the timing inside the Verilog. Without controlling the timing, the Verilog won't advance its flow. So we need to have a timing control also. There are three different ways you can control the timing. Like you can control using delay, or you can control using event, or even you can control using level sensitive. So we'll discuss all of them with different examples. And then finally, we'll have a live coding session to explain all these concepts in Verilog. So let's begin. So what is a behavioral modeling? We have already seen there are four different modelings that are available in Verilog, right? First one is switch level, second one is gate level, third one is data flow, and the final one is either algorithmic or you can call behavioral, right? So among all these things, the highest level of abstraction is behavioral modeling. Why? Because in the behavioral modeling, you can define your circuit in terms of functionality instead of logic gates or data flow. What I meant is, in the gate level, you can define the functionality by using primitives like AND, OR, NAND, like this. In case of data flow, you can use an assign statement and then you can assign the flow of the data to the register or wire, not register, wire, using some operators like this, A and B, something like that. But in the case of behavioral modeling, you can directly define the functionality of your circuit. Like if you want to have a functionality of inversion of clock, you can directly write clock is equal to inversion of clock, and this clock should be inverted always from the start to the end of the program. Then you can write always like this, always at the rate posage of clock. I will explain what are these things. You can write like this: clock is equal to clock, my clock is equal to my clock bar, right? So here it is very simple, right? You are defining a repeated statement, like you want to have this my clock is equal to my clock bar for repetition of from start to the end by using a simple single line of code, two lines of code, right? But in the case of gate level and data flow modeling, it is very difficult to define this kind of functionality. So that is why behavioral modeling is having high level of abstraction, because you can define the functionality of circuit by using Verilog codes. So that is about behavioral modeling. So why do we require that, right? We, whenever as a designer, we have to think and make a wise decision in the digital design in the early stage of the design, right? For this, you need to have various trade-offs in the architecture and algorithm before deciding the optimal design. Let's say you want to design some processor. In this processor, you have to try different kind of architectures to get to the optimal architecture. So trying different kind of architecture will require a lot of coding, right? If you do that coding in gate level or data flow, it will take so much of time and so much of effort. But if you do the coding in terms of functionality, like in the case of behavioral, it will be very easy to debug, as well as it is very less time consuming. So that is why behavioral modeling is used for complex circuits like processor or memory or any bigger circuit you want to design. And the hardware design in terms of algorithm, but not in terms of logic gates and data flow. As I already explained, here the hardware is designed, hardware is described in terms of functionality or algorithm, but not in the case of in the terms of logic gates and data flow. So that is all about behavioral modeling. Let's see how to write in behavioral modeling, how to write code in behavioral modeling. So first thing you need to know is there are two structured procedural statements called always and initial. By using these two statements, we can write or read, we can perform any operation in behavioral modeling. So these two statements are very, very essential to perform any operation in behavioral modeling. And all other statements appear inside these two statements. What I meant is all of the code that is present in the behavioral modeling will always be inside in these two blocks, initial and always. I will show you what are these two. And then we'll see the Verilog is a concurrent programming language, unlike the C, which is a sequential language. So what is concurrent and what is sequential? Let's say you want to write a thing like this: A is equal to B plus 1, C is equals to A plus 2, and D is equal to B plus 3. In C language, what happens? It will execute line by line. This is called sequential programming. First, it will execute A is equal to B plus 1, then it will execute C is equal to A plus 2, then it will execute D is equals to B plus 3. Right? This is sequential modeling. But in the case of Verilog, if you write the same thing, A is equals to B plus 1, C is equal to A plus 2, and D is equals to B plus 3, all the three statements will execute at the same time. This is called concurrent programming. So what happens in Verilog? Whatever the statements we have, they will execute parallelly but not sequentially, which is very, very important thing, and which is very, very useful thing in the case of Verilog. Because in the hardware, it's in the real world circuits, if you send the signal and if you have different circuits sitting here, they will all work if they are independent to each other. If the data is not dependent like this, if they are independent blocks, then they will all execute at the same time, right? Okay, let me draw clearly. Let's say you have a circuit like this, which has three different gates, and the data is mutually exclusive, right? It has three different outputs, and you want the three different outputs to be executed at the same time. So this is where the Verilog will helps you. If you write these three different outputs in Verilog, x is equal to A, B, C, D, E, F, then A and B, y is equals to C and D, then Z is equal to E and F. So what does Verilog do? Verilog will execute all the three at the same time. Instead of executing sequentially, it will execute concurrently. So that is the most advantage of Verilog compared to the C language, which is a sequential language. So each activity always or initial starts at time 0. What I meant is, if you have different initial blocks, let's say initial, you will define some statements here, begin and end. You'll use begin and end as a curly braces, and you will have one more initial block here, and you will have one more always block here. You will have one more always block. No matter how many initial or always blocks you have, they will always start at time is equals to 0. All of these blocks will start at time is equals to 0. Okay. No matter how many initial blocks or always blocks that are present in your Verilog code, they'll always start at time is equals to 0. And most important thing you should remember is they should not be nested. You cannot nest any initial block inside an initial block or always block inside an always block. Nested means you have one initial block and you have written some statements like initial begin count is equals to 0. Then again, if you want to do an initial inside this, it is not allowed. This will give you syntactical error. So nesting of the initial blocks or even nesting of the always blocks is not allowed in Verilog. Okay. So now we have seen the basics of the behavioral modeling. Let's go inside what are these two structured procedures. Let's start with initial block. What is an initial statement? An initial statement will have a keyword of initial, and all the statements that are appeared inside the initial statement. So begin is like a open curly braces and end is like a closed curly braces. All the statement, this is called a initial block. Okay. So the initial block starts at time is equals to 0, right? At time is equals to 0. That is what initial meaning, right? Initial means initialization. Initializing at time is equals to 0. and it will execute only once. This is the important property of initial block. It will only execute once when the simulation starts at time is equals to 0. If multiple initial blocks, then each block starts executes concurrently at time is equal to 0. That we have already seen, right? If you have different initial blocks, they will always start at time is equals to 0 concurrently, but not sequentially. They will all perform at single time. Okay. The main purpose of using initial block is to initialize any variables we have and is to monitor the signal, because monitoring can be we have already seen how to use the monitor statement. So we just need to write monitor statement once there is any signal change inside the monitor statement, it will always show you, it will always display the signal values, right? So for monitoring you just need once. So these kind of one time usable statements you can write inside the initial block. What are the one time usable statements? Either you can monitor the signals or you can initialize the signal, because initialization can be done only once, right? At the beginning of the program you will write, okay, I want to initialize my integer I to 5 or integer I to 10. That initialization statement can be used only once, so those kind of statements can be written in initial block. Okay. Now let's see an example of the initial block. Then it will be very clear to you how the initial block is working and how the timing inside the initial block is working, whether it is concurrently working or sequentially working, we'll see. Let's take different registers like register X, Y, A, B, and M. Okay. Now I am initializing my M is equals to 1 bit binary 0. And then since I am only using one statement, I don't need to write begin and end. I can directly write initial M is equal to 1 bit binary 0. Let's take one more initial block. Here I am initializing two different variables. So I am writing begin at 5 nanoseconds of delay. This we know, right? The hashtag is used for delay. So I am using 5 time units of delay. At 5 time units of delay, I want A to be 1 tick binary 1 and my after let's say 25 nanosecond delay, my B to be 1 tick binary 0. I have begin and I need to end this initial statement. So this is first initial, this is second initial, and I am writing one more initial. Here I am initializing X and Y data. Begin my X, let's say after 10 nanoseconds, I want my X is equals to 1 tick binary 0, and after 25 nanoseconds, my Y is equals to 1 tick binary 1. Okay. I have begin, so I need to end this, and I can write one more initial statement like this. Initial, let's say after 500 nanoseconds, I want to finish my program. See, I don't need to do the finish program always. I can write the in the inside the initial block. After 500 nanoseconds, it will automatically terminate the program. So this is one of the example where you can use the initial statement. Either you can use to finish the program or stop the program or even monitor the signals. Okay, how many initial blocks we have? 1, 2, 3, and 4. So as I already mentioned, all these 4 initial blocks will start executing at time is equals to 0. It is not like first I will execute this statement, then I will go to this, then I will go to this, it is not like that, because all the initial blocks execute concurrently at time is equals to 0. So let's draw time axis and we'll see what is the statement that is executing at what particular time. So this is my time and this is the execution of statements. Okay. So at time is equals to 0, what happens? As I already mentioned, all the initial blocks will start at time is equals to 0. So all these blocks will start executing. Since they have delays here in these 3 initial blocks, we have delays, right? Delays of 100, 25, 500, 5 and 25. So it will execute only after the delay. But in this initial block, we don't have any delay. So M will be executed at time is equals to 0. Okay, whatever m you have assigned, it will execute at time is equals to 0. So next thing will happen, this initial block will also start at 0, but there is a delay of 5 time units. So after 5 time units, this statement will execute. My A is equals to 1 tick binary 1. So this initial block will also start at time is equal to 0, but time unit is 10 seconds, 10 nanoseconds. So after 10 time units, I am using time units or nanoseconds. If my time unit is equal, I am assuming my time unit is equals to nanosecond. That's why whenever I say time unit or nanosecond, they both are same. Okay. If my time unit is 10 units, that means after 10 nanoseconds, my x is equals to 1 tick binary 0 will execute. Okay. Up till now, it is clear, right? This is also clear. Here only one statement is there, which is at 500 nanoseconds. So you can directly write after 500 nanoseconds, my finish will execute. So what happens to these two statements? At what time period they will execute? Let's think. Inside all the initial blocks are concurrently executing. That we have already seen. But inside the initial block, if you use this symbol, which is a blocking statement, I will explain what is a blocking statement. If you use this, then they will execute in sequential manner. Okay, what I meant is, first it will execute 5 nanosecond delay, then after it is executing 5 nanosecond delay at 5 plus 25 at 30 nanosecond delay, my B is equals to 1 tick binary 0 will execute. Okay. Similarly, this is starting at 0 and this x is equal to 1 tick binary is consuming 10 nanoseconds. From here to here 10 nanoseconds has passed. So after 35 nanoseconds, because 10 plus 25 is 35 nanoseconds, this statement will execute, right? Y is equals to 1 tick binary 1. This is very, very important. If you don't understand this, then you don't know how the timing is controlled inside the Verilog. So I am explaining one more time. All the initial blocks will start at time is equals to 0. So if there is no delay element inside the statements, then the statement will execute at time is equal to 0. That is what happened to M. Okay, the M is executed at time is equals to 0. Since there is a delay elements, so 5 nanoseconds of delay is there for A. So after 5 nanoseconds, A is executed, and after executing A, we have 25 nanoseconds delay. So 5 plus 25 at 30 nanoseconds delay, B will be executed, but it will not wait for 30 plus 10 because the initial blocks are start concurrently. So this initial block has already started at 0 and it will wait for 10 nanoseconds and the X is executed at 10 nanoseconds. Okay. Inside this, it will wait for 10 plus 25 nanoseconds, which is 35 nanoseconds. At that time period, Y will be executed. So the initial 500 will not execute after 500 plus 35 because this is also starting at 0. So it will execute at 0 plus 500, which is 500 nanoseconds. It will execute this statement. I hope this example is very clear to you. So this is the purpose of the initial statement. Once we know the purpose, we can see how to initialize using different combinations. Like you can initialize by 3 different methods. I will explain. I'm erasing this example. So what are the 3 different ways you can use the initial statements? First one is called combined variable declaration and initialization. So here we are combining variable declaration as well as initialization. So let me write. First one is combined variable declaration and initialization. Okay. So let me take an example for combined variable and declaration. So let's take, I have a clock of register type. So this is variable declaration, right? We know. And then I am initializing my clock is equals to 0. So here I am declaring the variable and here I am initializing the variable. So you can match these two statements into a single statement like this. You can directly write register, clock. I'm declaring the clock as a register, and then I'm initializing it to 0. So in a single statement, you can write both declaration as well as initialization. So this is called combined variable declaration and initialization. So this is also valid and this is also valid. Okay. So now let's take the other second one, which is called, the second one is combined port declaration and initialization. Here we have declared variable, but now we can declare port and then initialization also. Second one is combined port declaration and initialization. So let's take an example. So we know we can define the ports inside the module, right? Let's take sum and C out and A, B, C in. What is this? This is a full adder which is having 3 inputs and 2 outputs. So here I'm defining the ports, but not declaring what are the ports are. So I'm declaring the ports here. My output sum is, let's say, 3 down to 0 sum, and my output carry out is a single bit, and my inputs are A, B, C. A, B are 3 down to 0, and my C in is 1 bit data. So here I am declaring the ports. You can you can use initialization at the port declaration itself here like this. My sum is equals to 0 and my carry is equals to 0. So what I did is I combined both port declaration as well as initialization, right? Or you can use, if you don't want to combine them, you can just define the ports and then you can write an initial block, initial begin, because I'm using two statements. My sum is equals to 0 and my C out is equals to 0 and n. So instead of writing all these things, you can directly declare here itself. Okay, so this is called combined port declaration and initialization. There is one more way of defining the variables. The third method is called combined ANSI C declaration and initialization. So what does this do? In this second case, what we did, we have only defined the IO ports inside the module and we have declared them separately inside the module, right? But in the third case, what is called as combined ANSI C style declaration and initialization. So here, let's see what I am doing is I am declaring the ports as well as initializing inside the module itself. So it will be like this module. My module is, let's say, adder. I am declaring the ports. My output as a register of 3 down to 0 sum is equals to 0. See, I am declaring the port output, I am declaring it as a register as well as I am initializing. Okay. Similarly, this should be comma, not semicolon. Similarly, my output register of C out, which is a single bit, I am declaring it to 0. I am initializing it to 0. Similarly, I can declare remaining ports input 3 down to 0, A comma B comma input C. So this is how you can use combined ANSI C style declaration as well as initialization. So why there are three different methods? You should know the three different methods because in future maybe your coworker or your manager asks you to write the code in ANSI C style. At that time you should not tell I don't know what is ANSI C style. So this is called ANSI C style, where you can declare the port as well as you can initialize the port also. So the ANSI C style is particularly this thing. You can declaring the ports inside the module definition itself. Okay, this is called combined port. I usually prefer combined port initialization or combined port declaration and data initialization later. Okay, so you should know all the three different methods. Once you know all the three different methods, you can write your code for initializing any variables. Okay, this is all about initial statement. We have seen different examples also how to do the initial statement. Now let's move to the always statement. Right, this is what I have defined so far. There are three different ways: combined variable declaration and combined port data declaration and initialization and ANSI C style declaration. I usually prefer either of these two or mixed of these two, but not this. Okay. Now let's move to always statement. So what is an always statement? The name itself it is suggesting always, right? So it starts at time is equal to 0 and execute continuously in a loop fashion for infinite amount of time. It will execute until you ask it to stop. It will always execute. That is the purpose of always statement. That is what we require in real world circuits also. In real world circuits, what happens? Once you turn on the circuit, it starts working until you turn off the circuit, right? That is what we require in Verilog also. You need to have a statement which will tell once I start the simulation, it should run until I stop the simulation. That is where this always statements will help you. The always statements will start at time is equal to 0 and it will execute continuously in a looping fashion. Okay. Usually it is used to model a block of activity that is repeated continuously. For example, a clock generator. A clock inside a circuit will always exist, right? Clock will always flow inside the circuit. So to define this clock signal, you can use an always statement. How to define the clock signal using always statement? Let's take an example here itself. I want to show how to define the clocks in Verilog. So how to define a clock? What is a clock? It is just a digital signal which is varying between two different values, right? Like this, 1 and 0. Let's say this is logic 1, this is logic 0. It is varying from logic 0 to logic 1 continuously, right? And it has some time period. If it has a constant time period, then it is called clock signal. If it doesn't have any constant time period like this, okay, then it is called asynchronous clocks, okay, because it doesn't have any particular frequency, okay. So let's define this clock using always statement. How to define a clock using always statement? First of all, I want to define the clock variable. Let's say clock is a register. So I'm defining register, which is a output, right? My clock is an output. So output register clock. Okay. I'm defining my module, which is a clock generator. Module clock gen is my module. I want to generate this clock signal. That is the purpose of this module. So I'm defining it as a output. I don't require any inputs because I'm only defining clock as an output by using always statement. I don't require any inputs to get this. So output register data type, the name is clock. Okay, you can give any name. Let's say my clock. You can give any name. You should not fix with single name. You can give any name. So I'm defining my clock. First thing I need to do is I have to initialize my clock to 0, right? So this is where the initial block will help you. You can directly initial my clock is equals to 1 tick binary 0. So what does this do? It will initialize your clock variable to 0 at the beginning of the simulation. At time is equals to 0, your clock is 0. That is what we want, right? This is, let's say, time axis. At time is equal to 0, your clock signal is 0. That is ensured by this initial statement. Now, what I want always my clock should flip like this from 0 to 1 and 1 to 0, 0 to 1 and 1 to 0, 0 to 1 and 1 to 0. So that's why I'm using always statement. Always what I require, what is the time period I want? Let's say I want a time period of 100 nanoseconds. So in order to have a time period of 100 nanoseconds, I'm drawing it again here. Let's say this is my time period 100 nanoseconds, and if I want a 50% duty cycle, 50% duty cycle means the on time period and off time period both are same. They are exactly half of the total time period. So this is 50 nanoseconds and this is 50 nanoseconds, right? So what I am writing is I am writing always after how much nanoseconds it should flip? It should flip after 50 nanoseconds. After 50 nanoseconds or 50 time period, my clock should what is happening after 50 nanoseconds? It should flip or it should invert its data. So inversion of data is represented by using the unary operator. This this will do the inversion of the variable my clock. So what is happening here? First, it will initialize my clock to 0. Okay, at time t is equals to 0, it is initializing at 0. And then it will go to always block. Always block will also start at time is equal to 0. But since we have given 50 time units delay, after 50 time units delay, it will check this expression. What is this expression? It is just inverting my clock from its data. So earlier at 50 nanoseconds, it is 0. So it is inverted from 0 to logic 1. So now my clock will be logic 1 after 50 nanoseconds, right? And then the always statement will execute for infinite time, like in a looping fashion. So after this statement is executed, again it will go into the always statement and again it will wait for 50 nanoseconds. So it waited for 50 nanoseconds. Now my time period is 100 nanoseconds. At 100 nanoseconds, what happened? Again, my clock is flipping from 1 to 0, right? Because of this statement, my clock is flipping from 1 to 0. So now at 101 nanoseconds or 100 nanoseconds, you can see it flips to 0. Again, it will go inside the always block because it will loop continuously. So again, it will go inside the always block. Again, it will wait for 50 more nanoseconds. So 100 plus 50 is 150 nanoseconds. At 150 nanoseconds, again, it will flip from 0 to 1. The same thing will repeat continuously. That is how you can generate a clock period of any time period. Let's say you want time period of, let's say I want a time period of only 50 nanoseconds. How to do that? So for a 50 nanosecond time period, what should you write? You should write the delay as 25 nanoseconds because after 25 nanoseconds it is flipping. So this 50 will be replaced with 25 nanoseconds. That will create a time period of 50 nanoseconds. So whatever the clock time period you want, you can divide the clock time period by 2 and then execute this statement that will generate your clock statement. So let's generalize this thing. So how to generalize this thing? If I want a time period, so always remember generalizing the statements is very, very good if you are using Verilog or any programming language, right? The generalization will give you more flexibility. You don't need to go to that line again and then write different values if you can generalize the statement. What I meant for generalization is instead of using numbers, you can use a variable. Right now, I am taking a parameter. We know what is a parameter. A parameter is a data type which is used to define the variables, right? So I am taking a parameter called TP. TP is my time period. Let's say my time period is equal to 100 nanoseconds. I am initializing it to 100. Okay, I am defining a parameter and I am initializing it to 100. Now inside the always block, I can write after TP. I am not writing 100 here. I am writing directly TP. After TP, my clock is equals to negation of my clock. So what happens? After every 100 nanoseconds, it will flip. This is 100, this is 200, this is 300, this is 400, like this. So your time period is now 200, right? But you want time period of 100 nanoseconds. If you want time period of 100 nanoseconds, what you want to do? You can directly divide this by 2. So what happens? After every 50 nanoseconds, it will start flipping, right? Because 100 by 2 is 50. So it will flip like this. So what it is creating? It is creating a time period of 100 nanoseconds by using this statement TP by 2. Okay, this is how you can generalize. Let's say later in the coding, you will require a time period of 1000 nanoseconds. You don't need to go inside this always block. You can directly write 1000 here. That will convert your clock to 1000 nano period clock, right? This is what we call as generalization. Wherever there is TP variable, that will be automatically updated if you update that here in the parameter declaration. Okay. Now we have seen the example of always block and how to generate the clock using always block. We will use this clock generation circuit in the coming examples, because in order to give the stimuli, we will require the clocks, right? We have seen we can use clocks as a stimuli for resistors, for flip flops and all. So this is very essential. You have to build your own clock by using system clock that is available in that board. So how to build the clock? You can use these statements, like first you will initialize the clock, and then always you will try to flip the clock at whatever time period you want. Okay. Now there is one more important thing I want to show here. What happens if you put the initial, you you are using two different statements, right? Both initial and always to generate a clock. Why can't we do with single always block? You might think, why do I require this initial statement? Why don't I require, because I am initializing 0 and then flipping. So why don't I do that here in the always block itself? Like, let's say if I write like this, always my clock is equals to 1 tick binary 0, and then after, let's say, 10 nanoseconds, my clock is equals to negation of my clock. What happens if we write a code like this? So you can see, always it is taking my clock is equals to 1 tick binary 0, but not initial. That is the purpose of initial. In the initial block, it will only initialize at time is equal to 0, and then it will leave. It will leave the statement and it will go into always statement, and it will execute whatever you have written here. Whether you have written negation of clock or directly my clock is equal to my clock, it doesn't matter for the initial block. It will only initialize at time is equal to 0, and it will leave the statement. But in case of always block, it will always execute in a looping fashion. So if you write my clock is equal to 1 tick binary 0, initialization here, what happens? Every time it will initialize my clock to 0. So you won't get the clock signal, you will get a DC signal of 0, because every time it is initializing my clock to 0, right? So you should avoid initialization inside the always block. Always use the initial block. It is confusing, right? But remember like this, if the statement needs to be executed only once, then put it inside the initial block. If the statement needs to be executed forever in a looping fashion, put that inside the always block. Okay. I think it is very clear for you how to use the initial block and always blocks, because every statement inside the behavioral modeling will be inside these initial block and always blocks. So you should be aware how to use the initial blocks and always blocks. Okay. Now that we have seen how to write the initial block and always block, now we'll see how to assign the data in initial block and always blocks. This is called procedural assignments. Okay, it updates the value of register, integer, real or time variables. Okay, these are the different variables that you can update. Either you can update single variable, or you can update vectors also, like this register vectors you can update, or part of the vector also you can, like out of 5, which is a part of the vector, or bit select. This is bit select, right? Only one bit we are selecting. Or part is like this, 6 down to 4. This is a part of the vector. This is a bit select of the vector, and this is a complete vector. You can assign to either single register or vector, or bit select vector, or part of the vector, or integer, any data types, using these procedural assignments. Okay. What is its purpose? It places the value, and the value remains unchanged until the another procedural assignment places another value. Okay, which is unlike, this is in contrast to continuous assignments that we have seen in data flow. What we have seen in data flow? In data flow, I have a statement like this: assign my y is equals to a and b. So what happens in data flow? Whenever there is a change in right hand side of the variables, immediately the left hand side of the variable is updated, right? That is why in data flow the variable is always a wire, because this is always driven. Remember, it is very simple, because The output is always driven. So which data type will be always driven, whether it is register or wire? The wire or net we can call. It is an always driven data type because it is not waiting for anything. In case of register, it will wait and then it will drive the output. But in the case of wire, it will not wait. It will execute whenever there is a change in input. So the always driven data type like wire is used in terms of in case of data flow modeling. In case of behavioral modeling, we will use register, integer, real, and time variables. You cannot use wire in case of procedural assignments. If you use wire, it will give you a error or syntaxical warnings. You can check inside the Verilog code. Okay. So always use register for procedural assignments. We already seen the purpose why, because in data flow the right hand side expression to be continuously placed on the left hand side, but in the case of register it is not like that. It will be placed after waiting for some time period, and then it will place the data once the another data procedural assignment assigns to that thing, right? So there are two different ways you can assign. One is called blocking assignments and the other one is called non-blocking assignments. We'll see what is blocking and what is non-blocking assignments. So let's begin with blocking assignments.